Hi and welcome back. In this video we're going to be concentrating primarily on fossil fuels, those fossil fuels that are used extensively through society and the sources of them, as well as what reserves we have available in Australia, as well as the environmental impact and some key factors in relation to their refining and processing. So let's get started. Essentially, after this video, you should be able to address the following learning objectives. This is, you should be able to define the terms fossil fuels, renewable and non-renewable. Okay, outline the sources of fossil fuels and the main fossil fuel reserves found in Australia. Be able to explain the difference primarily between black coal and brown coal in terms of energy and pollutants, as this is one that often comes up in exam questions. Explain the process of fractional distillation, the processing of crude oil. This is going to be primarily bonding based, so you should be able to explain the process with respect to the role of intermolecular forces between molecules and their subsequent boiling points in terms of how we separate them. Then finally be able to discuss the key environmental considerations regarding the use of fossil fuels and challenges these provide. You should be familiar with the composition of each of the fuels that we're going to go through, and the basics on how they're obtained and what their environmental impact would be as a result. So make sure that you take notes on those as we go through. So of course, fossil fuels are the result of a long-term process within the Earth's crust. In this case, when we're talking about oil and gas, we're talking about products that have arisen due to mass die-off in primordial oceans. So you're talking 300 to 400 million years ago. Mass extinction events means that we have a large number of organisms which have died and laid at the bottom of the ocean floor. These have subsequently been covered in sediment, leaving sedimentary rock on top. This gives us heat and pressure. So over time, this converts the carbon-based materials in those life forms, carbon, hydrogen, nitrogen, oxygen, etc., into oil, okay, and natural gas. Generally, we tend to find natural gas reserves above crude oil. So you have the crude oil trapped within the stone or in reservoirs in voids, and you will have natural gas trapped above that. Historically, natural gas was quite often allowed to escape on the tapping of a new well. It wasn't considered to be a prime commodity to be collected. These days, with diminishing reserves, we find that the natural gas is quite often collected as well. As for coal, we're talking about plant material, okay? So with oil, it's animal matter. With coal, it is plant material. So swamps, prehistoric swamps and things like that 100 to 400 million years ago, lots of plant die-off. Those plants, again, sediment lies on top. The vegetation will turn into peat, and you may have heard of the peat bogs in Scotland and places like that where we get a lot of archaeological finds from the Iron Age and the Roman Age through the UK. The next stage from that peat is more time, more pressure, more heat, and that peat will turn into solid coal, which again is mined generally by putting down large mining pits and mechanical extraction. So coal's going to be the first one that we look at. So coal has a number of different considerations that go along with it. We just saw how it has formed over time, heat, pressure, millions of years, we end up with coal seams. So this is what we have here. Okay, it is a mixture of molecules with masses as high as 3,000 atomic mass units. Okay, we don't tend to use moles for the measurement of fuels because they are often mixtures. Okay, so because they're not pure substances, they're often mixtures, so we will have grams per litre, or we will look at different measures because we can't have a molar mass for an impure substance, and these are often mixtures of many different compounds. Coal will contain mixtures of carbon, hydrogen, nitrogen, and sulfur, along with trace amounts of other elements. Black coal has the highest percentage of carbon compared to brown coal. Brown coal is still quite wet, so it has a higher percentage of water. Okay, and that affects the amount of energy that it will give off. So it doesn't burn as cleanly because, first of all, when we set light to the brown coal, we need to drive off that water in order for the coal to truly burn. And as we know, water has a high specific heat capacity, so it'll absorb a lot of the initial energy from the burning. So we see a lower energy output for brown coal than we do black coal. And in fact, a lot of the reserves we have in Victoria are actually brown coal, which is particularly bad, and why we look to move away from that into renewables. Essentially, with all fuels, we're looking at combustion reactions, and with coal, it is the carbon that is burning, so we represent the combustion reaction for the desired product. In this case, it's carbon reacting with oxygen to give us CO2, this being complete combustion. Okay, remember, with incomplete combustion, we would have a mixture of carbon monoxide and other products. In addition to this, because the coal is not pure and we have other elements in here, we will get soot and ash, which are solid particulates that add to bad air quality and things like that. We of course get water, which is a product of the combustion reaction, and we also get sulfur dioxide and sometimes nitrogen dioxide being produced as a result of the burning of these impurities within the coal. Delta H is the amount of energy that's given off per mole of this equation, and we'll talk about thermochemical equations a little bit later on. But essentially this is saying that we get 33 kilojoules of energy given off for every gram of coal that we burn. Coal has been used extensively since the Industrial Revolution, the beginning of the railways. And we know it gives bad pollutants, which led to the Clean Air Act in England way back at the beginning of the Industrial Revolution. It exists in large deposits which are fairly close to the surface, or were. We're digging deeper and deeper these days as we use up some of the coal, and it accounts for 90% of all the world's fossil fuel reserves. Coal is used extensively in power plants, for the generation of electricity. A lot of our power plants worldwide are coal-fired power stations. In fact, Latrobe Valley is full of them. And it accounts for about 40% of all fossil fuels consumed worldwide. In comparison, natural gas and oil will tend to burn cleaner and produce less smoke, but we have smaller reserves and they're harder to get hold of. Also, oil doesn't work particularly well in the type of electric power stations that we have at the moment. Oil, okay, so when we refer to oil within this area of study, we're talking about a mixture of hydrocarbon molecules. We're talking about crude oil that are members of the homologous series of alkanes. So typically we're talking about molecules that will contain carbon-carbon single bonds only. You'll notice that when we refer to the carbon-carbon single bond, we have used this notation here, and this is fairly standard for using explanations as we move through. These oil wells, or dirks, pump oil out from below the surface that is then collected. Crude oil itself does not burn very easily at all. It has a very, very high flash point, so we don't see crude oil boiling. It's not useful as a fuel itself. We need to process this further as it contains many different compounds. Octane, which we use for fuels, for airplane fuels and things like that, and many other hydrocarbons in petroleum products. This here is the combustion reaction for octane. You should be familiar with the process of drawing and balancing combustion reactions. Typically, when we're talking about for the production of energy, we're talking about complete combustion. Of course, the amount of energy we get out from a reaction will reduce if the combustion is incomplete, because not all of the energy is going to be given out to the system. So the compounds are separated by the process of fractional distillation and then changed chemically by cracking. Within the scope of this course, we won't look at cracking very much. It is just the process by which we manipulate the chain length so we can make them smaller or larger depending on the mixture that you get from the crude oil itself. The largest reserves of crude oil are predominantly in the Middle East. Australia does have some oil reserves. The reserves are much smaller than coal these days, and we do have a limited time span on that. The estimates are about 40 years, with Australian reserves expected to run out in 10 or 20. This changes as our use of fossil fuels changes in society as well. So these tend to get further and further out, with the less that we use in society being replaced by other forms of energy. About 90% of the crude oil for Australian needs is imported. We do have some significant natural gas reserves, but we do import the majority of our oil for petroleum products. This video here will quickly go through fractional distillation over about 4 minutes, and we'll just let it run and have a listen.
In this video, you will learn how fractional distillation separates crude oil into useful fractions. Crude oil is the term used to describe unprocessed oil. That is oil that has been taken directly out of the ground, either on land or under the sea. It is an exceptionally valuable resource. It provides us with a great number of hydrocarbons, some of which are useful as fuels, and others are used in the manufacture of many different chemicals and even plastics. However, in the raw form as crude oil, it can be a viscous, dark-coloured tar-like consistency, and the different fractions of hydrocarbons must be separated by fractional distillation for them to be useful. Before we understand how fractional distillation works, we should be clear that crude oil is a mixture of hydrocarbons with different chain lengths, some being short molecules and some being very long. Intermolecular forces act between molecules, and the longer the molecule, the greater the intermolecular force. As you can see here, the small molecules have weaker intermolecular forces, and so will require less energy to break them apart and turn them into a gas. They have a lower boiling point. The longer molecules have greater intermolecular forces. More energy is required, a higher temperature will be needed to evaporate these molecules. They have a higher boiling point. Now we understand how chain length is related to the boiling point of a molecule. Let us look at how this method works. As you can see, crude oil is heated up to a high temperature outside of the fractionating column. The hot crude oil, now mostly in vapour form, is pumped into the column. The column has a heat gradient and is very hot at the bottom, going cooler as we move up to the top. Even at the very bottom of the column, where the temperature is still high, some long chain molecules with high boiling points begin to condense back into a liquid. These are collected at the bottom of the column. The rest of the molecules start to rise up the column, making their way through bubble caps in each tray. The bubble caps slow down the rate of the rising vapour, and eventually the vapours get too cool, condense, and are collected as liquids in the trays. Small molecules have low boiling points, and so condense much higher in the column, where the temperature is cooler still. As you can see, hydrocarbons with similar boiling points are collected in the same tray, and this is why they are known as fractions. They are mixtures of hydrocarbons with similar boiling points. Each fraction has some important uses. Some examples of fractions are petrol, useful as a fuel for cars, naphtha, used in the manufacture of chemicals, kerosene as aircraft fuel, diesel oil, used as fuels for vans, cars and lorries, and bitumen, a mixture of large chain hydrocarbons used to lay roads. Now, at the end of this video, you should understand that crude oil is a mixture of important hydrocarbons, and that fractional distillation is the method used to separate crude oil into useful fractions with similar boiling points.
Okay, so that's our review of fractional distillation. It's unlikely you're going to have to be able to talk about each of the fractions, but you should be able to talk about the temperature decreasing as we rise up the column, and therefore the smaller molecules with the lower boiling points, which will be gases at those temperatures, accumulate at the top, and our larger molecules are taken off in the fractions at the bottom. Okay, so this allows us to separate the molecules in terms of boiling point. So this gives you a summary of the different products that we obtain from the cracking of crude oil and the purification of crude oil through fractional distillation. You, again, don't need to know the name of the different fractions, but it does give you an idea of the different types of molecules that we get. Hopefully one of the things that you will have noticed with this is that the viscosity of the compounds also increases with chain length. Viscosity, of course, being the resistance to flow of a substance. So honey, if you think about honey, this is a very viscous liquid. Okay, it is thick and quite gloopy, whereas water has a very low viscosity. Okay, so these are the two that I like to remember to remind me about viscosity. And so the same thing goes here. Large molecules with strong intermolecular forces will be more viscous. So one of the main reasons that we're concerned about all of this in terms of fossil fuels, because they're non-renewable, we can't make more in a short period of time, and we are finding less and less reserves of them over time. It means that we do have this risk of running out, and we rely on fossil fuels, particularly petroleum products, to provide a mobile source of energy. We have come up with many sources of energy alternatives for in-place energy, so solar power, tidal, and all that kind of thing. But in terms of movable energy for transportation, we are still very much reliant on oil. Okay, the third of our fossil fuels is natural gas. Natural gas tends to be a mixture of methane with small amounts of ethane and propane in. This is the gas that we see powering our Bunsen burners in the laboratory. It has small amounts of sulfur, CO2, and nitrogen, but less than what we see in crude oil. It's typically used for heating and cooking, i.e. gas cooktops and things like that. Some gas power stations do exist, and the Australian government has looked at looking further into natural gas powered power alternatives in the coming few years. It's one of the alternatives that Scott Morrison has been looking at and talking about recently. There are limited reserves. They often found in conjunction with other fossil fuels. So over coal seams or coal seam gas is also natural gas, and shale gas. These are all talking about the same kind of thing, mixtures of methane. Again, when we're talking about fuels, we're talking about combustion reactions, and we are given the combustion reaction for methane here, which is the main component of natural gas. Liquid petroleum gas is a liquid form. Again, this time it's not methane. This is usually under pressure. This is what we use in our barbecues and lighter fuels. These are propane and butane, so this will be C3H8 using that CnH2n plus 2 rule for alkanes. And of course butane, but being 4, C4H10 for butane. These gases are under pressure. Under pressure, they become liquid. Butane is at the interface between a gas and a liquid at room temperature. So these will liquefy, and when stored in containers will be stored as a liquid, so we can use them for, they're safer to transport than gases under pressure. This one here talks about fracking, and we'll talk about fracking more in class in terms of environmental impacts. You may have heard about this in terms of methane gas reserves going through water supplies and lakes catching on fire, and this is a result of fracking. So fracking is where we use water to push out residual gas supplies, and we will talk about this a lot more in class. But again, this is another way that we can source methane gas from below the surface of the ground. And then some more details for you here on the way that fracking works. This is using water to push out the gas. So we inject high pressure water to push out the gas from the system, giving us a mixture of methane and water. if this gets into the water table, as you can imagine, it has quite significant environmental impacts as we end up with hydrocarbons polluting the water system. Okay, this last one here is just a quick multiple choice question for you to review and have a go at, and then we're done. This has been quite a long video as it is. So have a go at this one here and you will find the answer in your slides on the next slide. And that's it from me. I will see you in class and hopefully you have some good notes on fuels.